Thanks, Ashwin, for the introduction. Hi, I'm Kaushik, and today I'm going to give you a demo on how to simulate the flow past a GCM tractor trailer using SankhyaSutra Labs flagship offering, which is known as SankhyaSutra Taral. So the agenda for this meeting is as following. So I'll just walk you through what exactly SankhyaSutra Taral is and why and where it can be used to satisfy your CFD needs. I'll then give you a brief background on the emissions that are caused by heavy duty vehicles, which are known as HDVs. I'll then run you through the simulation workflow and the process that is needed to set up a particular case using SankhyaSutra Taral in order to run your simulation. I'll then show you a hands-on demonstration of running the simulation of the GCM tractor-trailer geometry on the product itself. To give you a brief background on what the Lattice-Boltzmann method is about, it differs from conventional CFD solvers in the sense that it doesn't have necessarily discretized the Navier-Stokes equation in order to arrive at a solution. It rather deals with the Boltzmann equation or a variant of it, where your space is discretized by a finite number of discrete velocities. You have points at certain locations in space, and you basically restrict your particles at that particular point to move in certain directions. These are known as pseudoparticles, and they are represented in the Lattice-Boltzmann method by a particle distribution function. They move and collide on a lattice according to certain rules that are stipulated by the method itself, and these rules are also derived from the law of conservation of mass and the law of conservation of energy as well. You can also use higher order models. You can also use different variants of these discretized velocity models in order to simulate flows at different regimes. For example, you might want to use a lower order model or a model with relatively fewer velocities in the discretized velocity space to simulate a laminar flow. You might want to increase the number of velocities that you discretize your velocity space with for a more turbulent flow, or for a flow which essentially is characterized by a higher Mach number. The USP of SankhyaSutra Taral is that we guarantee numerical stability without the use of turbulence models. We essentially close our equations with the help of first principles and the second law of thermodynamics, which I'll get into further in consequent slides. Another feature that makes our grid efficient and good for employing your solutions with is our BCC lattice structure, which I'll also talk about in consequent slides. So the entropic method is basically derived from the second law of thermodynamics, and we essentially make use of that for our collision dynamics in our version of the Lattice-Boltzmann method, which is known as the entropic Lattice-Boltzmann method. We also make use of the body-centered cubic mesh, which is different from what is employed in conventional Lattice-Boltzmann methods, which is known as a simple cubic mesh. And the body-centered cubic mesh has been shown to have 4 to 6 times less discretization errors, especially for complex curve geometries, as compared to the simple cubic mesh, with only twice the amount of memory that is needed as compared to the SC mesh. We are also known for being able to simulate cases at high Reynolds numbers and high Mach number flows, because we have a wide range of Lattice-Boltzmann models to offer to the user. And last but not least, we make use of novel data structures and efficient space packing data structures in order to extract maximum performance from whichever hardware our product runs on. Yes. So as I spoke about in previous slides, the key features and benefits of making use of SankhyaSutra Taral for your CFD needs are that we are able to obtain solutions to the underlying physics without the need for any approximations or turbulence models, where there's a huge dependence on the kind of grid that you use and the amount of compute that you throw at your particular solution. We also offer automatic generation of structured grids with local refinement that can be specified by the user according to their needs and desires. The user can either specify spatial regions where they want specific locations in their domain to be resolved with specific resolutions, or they can designate a particular resolution for a surface of their interest in the geometry that they make use of for the simulation. SankhyaSutra Taral can also efficiently handle complex and arbitrarily moving geometries for simulating moving geometry flows. And as I said, it can also run flows with high Reynolds numbers and high Mach numbers. It has several LV models to offer with varying numbers of velocities, varying numbers of discrete velocities, which essentially translate into a wide array of higher order LV models that are available for the solution. And the data that the freedom that we give to the user to save data of interest in the format that they desire grants the ability to easily extend their applications to be able to post-process the data to arrive at aeroacoustic conclusions, and to also use the same data to perform other multi-physics simulations. Now, to give you a brief background on HDV emissions and why it's relevant in today's world, around a third of our carbon dioxide emissions are caused by the transport industries, which are basically the transport via the land, sea, and air methods. And motorized transport on land, sea, and air is, of course, as we all know, heavily dependent on internal combustion engines. And these engines operate at an efficiency of only around 40%. And as you can see on the graphic on the right, 50% of this energy is used to overcome aerodynamic losses. While trucks and buses make up only around 8% of the total number of vehicles that ply on land, they contribute to an approximate number of 35% of the total emissions that are caused by vehicles that are on land. So that is a very huge number for the sheer percentage of vehicles that these particular category of vehicles make up. And as we know, there's stringent restrictions that are coming in from all points in the world with respect to climate change and reducing emissions and being able to achieve zero net emissions by the year 2050. And aerodynamic efficiency plays a huge role in being able to reach this particular target, and in the EVification of trucks and buses alike, which is going to play a huge part in being able to reduce emissions and reach net zero emissions by the year 2050. Which brings me to the motivation to use our particular solution to be able to solve this problem. So, in order to study the aerodynamics of any particular geometry, wind tunnel experiments are the most prevalent method in this particular in this particular year right now. And there is an urgent need for alternative and feasible, low-cost, accurate numerical solutions. Currently in the industry, RANS is the most commonly used solution, as it's easy to employ and does not need a lot of complexity in terms of being able to run simulations, and also doesn't need a lot of compute as well, because it employs a lot of wall models, etc. But there's a certain set of limitations that come with running RAN simulations, as specifically for automotive geometries, the most important region that you want to be able to predict accurately in order to compute your drag force accurately is the wake of the vehicle, which is the region behind the vehicle. And RANS especially has a huge limitation when it comes to this, as unsteady phenomena are vital in being able to predict the base pressure, and thus are vital in being able to predict the drag force that a particular automobile experiences. The next obvious solution that anybody will land on is to run DNS simulations, but this is extremely infeasible, as it's quite expensive to be able to run DNS simulations for automotive geometries, as the number of grid points is of the order of the cube of the Reynolds number that characterizes a particular problem. And for for simulations that pertain to automotive geometries, the Reynolds number is of the order of 1 million. which takes the memory requirement for to be able to run DNA simulations for automotive geometries to be of the order of several hundreds of terabytes. The most obvious solution, after taking into account all of these limitations and considerations, is to be, excuse me, is to run simulations with LES models. And while this is a good solution, there's also a con when it comes to using these methods, as the accuracy of your solution is again highly dependent on the choice of turbulence model that the user employs. Which brings me to the offering that SankhyaSutra Labs has, which is SankhyaSutra Taral. It makes use of the entropic Lattice-Boltzmann method. It has been shown to be inherently stable for high Reynolds flows without the need for any explicit turbulence modeling, as the solutions that we arrive at are derived from the second law of thermodynamics and thus are derived from first principles. Now, to give you a brief idea of why the GCM tractor-trailer geometry was synthesized, it was developed by the US Department of Energy in the year 2006. It is a 1:8 scale model with numerous simplifications that render it easy to mesh and run simulations for. The basic purpose of creating this geometry was to be able to have a valid case to facilitate validations for CFD codes. It's essentially a simplified tractor geometry with a trailer that is attached to its rear. The trailer has a simplified underbody, and this case has an abundance of experimental data that is available for comparison, which makes it a very good case to validate your particular solver against and to gain a deeper understanding into truck aerodynamics and what exactly contributes to trucks having such poor aerodynamic efficiency compared to other streamlined bodies. This is just a deeper look into what the geometry looks like. It's essentially made up of three parts in terms of aerodynamics. The first part, which the flow hits first, is the engine and the cab. And in this particular configuration, the engine is placed in front of the cab. There's different classes of trucks where the engine is placed behind the cab, and uh, that's one of the characteristic features for defining which segment your particular truck geometry falls into. One of the major reasons, spoiler alert, for the enormous amount of drag that this particular geometry experiences is the gap between the tractor and the trailer. And there's several aftermarket solutions for this kind of a problem where there's paddings that you can put in between the tractor and the trailer in order to improve your aerodynamic efficiency. And finally, the most important part of this particular entity is the trailer, where this is also a huge contributor to the drag force that this particular geometry experiences, as it causes separation over the rear over the rear end of its geometry, uh, which leads to the major component that any automotive geometry experiences as drag, which is the pressure drag due to separation over the rear end. Now, I'll be talking in brief about what the simulation workflow for a typical example in SankhyaSutra Taral looks like. The first step is to import a clean geometry, and the first step in any CFD workflow as such is the pre-processing step, where you pre-process your geometry, you fill any holes, etc., and you import the geometry itself. And the format that SankhyaSutra Taral supports is the STL format, the STL ASCII format, which is essentially a list of triangles that make up your particular geometry. Then there's four categories of parameters that the user needs to specify. They're known as the grid parameters, fluid properties, measurement parameters, and global simulation parameters. The grid parameters have to do with what the user needs to specify in order to characterize the grid that the simulation runs on, such as resolution, domain, etc. The fluid properties are the material properties of the fluid which the user wants to employ in their particular simulation, which are density, molar mass, etc. And what we call measurements are essentially dumps of data at user specified frequencies that the user might post process to achieve their quantities of interest. And last but not the least, we have the global simulation parameters, which is the total amount of time in the simulation frame that the user wants the simulation to run for, and other parameters such as the global project resolution, etc., which I'll talk about in more detail while I'll be doing the hands-on demonstration for you. And finally, SankhyaSutra Taral also has a post-processing tool in which the user can obtain slices and uh, view their view their solution field directly without having to download the data and move to other tools. But that option is still given to the user where they are free to download their data and view it on third-party tools. Talk about the pre-processing step. For simpler geometries such as sphere cylinders, etc., we we give we give the user the chance to generate those geometries directly on the SankhyaSutra Taral GUI. You can also create these basic shapes on ParaView and export them as ASCII STL files, which you can then import into the GUI tool itself. For complex geometries, what we recommend is that you generally clean your CAD and generate your CAD from third-party CAD tools and tessellate these models as triangulated meshes and save them as STL ASCII files. You then import these geometries into the SankhyaSutra Taral solver itself, which performs some basic sanity checks on the STL file automatically. Then you set the simulation parameters. To start with, the grid parameters have majorly to do with the resolution of the grid, the extent of the grid, etc. Patch-wise resolution basically refers to the resolution that the user wants to specify on a specific region of their STL file. So your STL files can be divided into different patches. For example, if you have a cuboidal domain and you want your you want the top plane of your cuboid to have a certain resolution which is different from the rest of the domain, you are free to specify that as a user. By brushes, we give the user the facility to specify certain to designate certain cuboidal regions in their domain that they want resolved with specific resolutions of interest. And the number of refinement levels, which is basically the number of jumps the grid does from the finest resolution to the coarsest resolution, is automatically determined by the solver, and the grid is generated automatically based on the user inputs of the resolution on the patches and surfaces alike. We then have to set the properties for the fluids, for the fluid that the user employs to run the simulation, which are density, the kinematic viscosity, and molar mass. We then have measurement parameters, which are basically which basically the user can specify to dump certain kinds of data at specific uh, uh, times of interest. And then come those global simulation parameters, which are the kind of quantities that the user wants to monitor during the simulation, such as forces and macro quantities such as density, velocity at specific points. The user also has to set the boundary conditions at all patches of the STL, the initial conditions for the domain, and the total simulation time that the user wants the simulation to be run for. We also provide a facility to be able to dump restart instances of your simulation at specific points in time so that the user can restart that simulation at any later point of time as part of a fresh run. Now, I'll just give you a brief account into what the simulation parameters for the GCM flow at a Reynolds number of 1.15 million are for a angle of 0 degree yaw. So there's two discretization strategies that the user can employ. They can either make use of a single resolution grid where the resolution is the same across the domain, and while this might lead to a high cost of simulation, this might be more accurate for certain cases. But what we offer is a multi-resolution simulation discretization strategy where the user can uh, designate their geometry to have a fine resolution and can choose to have a coarser resolution farther away from the geometry, where where the level of accuracy that is needed is not as high as what is needed very close to the geometry. So this retains accuracy while decreasing computational cost. The domain dimensions for the simulations have been given in accordance with NASA's experiments, which have been performed in a 7 by 10 inch squared wind tunnel. You can refer to these dimensions in the reference that is given at the bottom of the slide as well. As for the material properties, we've employed the same material properties as was given in the reference itself, which is air at room temperature, a Reynolds number of 1.15 million, a Mach number of 0.15, and a simulation time of a total of 0.5 seconds. These are the dimensions of the geometry. The inlet velocity is 52.5 meters per second, which is based on the Reynolds number, and the initial conditions for pressure and temperature are identical to the boundary conditions as well. The boundary conditions essentially are a constant velocity inlet at the x minimum plane, a static pressure outlet at the x maximum plane, and no slip walls for all other patches. I'll just quickly jump to the GUI tool itself so I can show you a quick demonstration of how to perform simulations in SankhyaSutra Taral for the GCM Tractor-Trailer geometry. So this is the loading screen for the SankhyaSutra Taral tool itself, where you just type in your username and password, which will be given to you by the administrator, and click on the login button. Then this is the dashboard where there's a list of projects with user-defined descriptions and other information that might be relevant to the user. We also have information on how much data your particular user account uses. I am using data of 280 gigabytes for my specific account because I've run other simulations in the past. You can also choose to share projects with other users and vice versa. For example, okay, there don't seem to be any project shared with me, but if somebody else has shared a specific project with you, then you will be able to look at it here. So I'm going to jump right into creating a new project for these particular simulations. So I'm going to click on the new project button. I'm going to give it a title. I'm going to call it GCM Webinar March 28th. I'm going to give it a brief description. Simulations. Geometry. The unit system can be set here. Currently, the only unit system we support is the SI unit system. I'm going to click on Create Project to create this project. So once the project has been created, it should show you. It should show up in the list of projects on your dashboard. So as you can see, this has been created here. To go to the workspace where you can edit simulation parameters, you can click on Open in Workspace. This is the main screen. Nothing has been loaded yet. This is a rendering screen, so you can't see anything here. So the first step that I'm going to do is to import my geometry. So this is a pipeline where you can see all of the relevant categories that need to be set, for which the parameters need to be set by the user. So I'm going to click on the plus beside the geometry tab and click on import. So I have the geometry ready, and in Taral, the expected geometry is in the following format. It's in the ASCII STL format with the patches for the cuboidal domain also present in the STL file. So I'm also assuming that it is understood that the STL has to be in SI units. So I'm not going to use any of these transformation options, but the user has the option to scale, rotate, or change the position of the geometry that they import. For other basic geometry shapes that the user might want to create, there's a create button where you can create primitive geometries such as spheres, cylinders, and cuboids. Since I'm not going to do that, I'm just going to click on OK directly to import the specific geometry. Right. So we can see that the geometry has been imported along with the cuboidal bounding box that is representative of the wind tunnel in which the experiments for this particular case were run. So this is the truck geometry, and I'm going to click on the negative Z view to get a side view of the geometry. And Taral, as I said, gives you the option to set custom resolutions at specific surfaces in your STL. So what we call patches are essentially surfaces in your STL file. So my STL file will essentially have 6 + 1. 6 I say because 6 faces of the cuboid that are representative of the wind tunnel, and 1 for the patch or the surface that makes up the truck geometry itself. So my STL file will have 7 patches or 7 surfaces. So I want to set an extremely fine resolution for the surface that corresponds to the truck itself. So I'm just going to directly jump into GCM, which is the surface of the truck, which is highlighted in red here. So I'm going to click on set resolution. And since I'm already familiar with this case, I'm going to set a resolution of 2 millimeters. This resolution estimate is based on being able to resolve the Taylor microscales that are characteristic of this particular run, which are again determined by the Reynolds number that defines this run. So I'm going to set the resolution and just click on OK. So the resolution has been set, and for all other patches, I would want them to be them to be matched at the project resolution or the course's resolution, which is one of the global parameters that we'll set at the end. Right. So in SankhyaSutra Taral, we essentially have regions which are basically regions that are characterized by disjoint volumes that is separated by STL surfaces. So for example, this particular geometry has 3 regions. One region that lies inside the truck geometry that is separated from the rest of its universe by the surface of the truck geometry. One region that is characterized by the volume that lies outside the truck geometry and inside the cuboid, and the outside region which is characterized by the region that lies outside the cuboid. This outside region is added to the solver by default, and the input that this particular parameter needs is any coordinate that lies inside this particular region. So for outside region, I'm going to select the geometry that this region is associated with. I'm going to set the coordinate as some 6, 0, 0. As you can see, the coordinate can be visualized by increasing the point display size. And SankhyaSutra Taral again has 2 different kinds of regions, which are simulate and vacuum regions. Vacuum regions are regions where we don't solve the Boltzmann equation and thus do not like allocate blocks themselves. Whereas simulate regions are the regions where we solve those equations and arrive at the quantities of interest that are specified by the user. So I'm just going to click on OK. And I'm going to add the fluid region, which is the region that lies outside the truck but inside the wind tunnel, which is the region of interest for the user. I'm going to give a coordinate of just a second. I'm going to give a coordinate of -2, 1.5, 0. So that lies inside the domain in the fluid region. And I'm going to set the kind as simulate. Click on OK. And I'm going to add a region that lies inside the truck. I'm going to name it bulk. Select the geometry that it's associated with. And set the coordinates of the point that lies inside the truck geometry. So as you can see, this lies inside the truck geometry. I'm going to set the kind as vacuum and click on OK. Now, as I explained before, the wake of any automotive geometry is probably the most important region to be able to predict drag accurately. And SankhyaSutra Taral gives the functionality to be able to set a custom region with a user-specified resolution, so that the solution in that particular cuboidal region is of a higher accuracy than whatever we would get with a coarser resolution. So I'm just going to set a brush for the wake of this geometry. So the cuboid that defines this brush is characterized by the coordinates of the minimum and the coordinates of the body diagonal that runs across from the minimum maximum point of the cuboid. So since I'm already familiar with this case, I'm just going to set the bonds directly. As you can see, this is the brush that is set. I'm going to give it the same resolution as the patch that I gave, as the resolution that I gave for the GCM patch. And I'm going to click on OK. Now, I'm going to set. Okay, so these global parameters have to do with a tool that is going to be covered in subsequent webinars, which gives the user to be able to have a glance at what their mesh will look like before starting the actual simulation itself. But for now, I'm just going to directly jump into being able to set parameters to run the simulation itself. So I'm just going to add a material to my simulation library. I'm going to choose air, because that's what I want to run my simulation with. I'm going to set the initial conditions that correspond to the Reynolds number of 1.15 million. I'm going to give it a name called initial underscore condition. The region that this particular IC is associated with is the fluid region, and the velocity is 52.5 meters per second, which corresponds to a Reynolds number of 1.15 million, and a temperature of 298 Kelvin, which corresponds to room temperature. We're going to click on OK. So the boundary conditions pipeline is automatically populated by the solver itself, and all we have to do is go into each individual BC and set the type of boundary condition that we want to be applied for that particular patch. The other parameters that need to be set in the boundary conditions tab are these parameters that are known as from region and to region, which essentially determine the direction in which the boundary condition is applied for that particular patch. So for this particular patch, I would want my boundary condition to be applied on the points that lie in the fluid region and not the bulk region, which lies inside the GCM domain. So to be able to communicate to the solver that is where I need my BC to be applied, I'm going to select my from region as the bulk and the to region as the fluid. So that instructs the solver to select the boundary points in the fluid region on the GCM surface itself. And the surface is already selected as GCM, and I want the no-slip wall boundary condition to be applied on the surface. So the other kinds of BCs that we offer are the free slip BC, the outlet BC, which is a static pressure outlet boundary condition, the inlet BC, which is a constant velocity inlet boundary condition. Symmetry is the symmetry boundary condition, and wall is the no-slip boundary condition. We also offer periodic and the moving wall BC for your rotating or oscillatory needs. So I'm just going to click on OK, apply. I'm going to go to Xmax, which is this plane. I would want to apply the outlet boundary condition here. So I'm just going to go into this and select outlet. The from region again is outside, and the to region is fluid. Outside because I want my boundary points to be on this side of the domain, and this is the region this surface separates the outside region and the fluid region. So I'm just going to click on apply. Then I'm going to go to Xmin, select the inlet BC. From region again is outside, to region is fluid, and the speed is 52.5 meters per second, which corresponds to the Reynolds number of 1.15 million. Click on apply. And the rest of the surfaces have the wall boundary condition. And SankhyaSutra Taral gives the option to be able to copy one boundary condition to several other boundary conditions. So I'm going to copy BC underscore GCM, which is a no slip wall BC, to all of the other patches where the no slip wall BC is to be applied. So I'm going to select Ymax, Ymin, Zmax, and Zmin and click on copy. And for just to check, I'm just going to go to Xmax and see if this has been applied properly. So Zmax is fine, wall is fine. Oh, but this is not bulk. This is supposed to be outside. Sorry. So I'm just going to go into each BC and change that specific part. Zmin, outside, and okay. So we have our initial conditions set, we have our boundary conditions set, and we have our material properties set. The penultimate step before we run the simulation is to define measurements, which is basically to tell the solver to print certain kinds of data in certain kinds of formats at user specified time frequencies. So we offer the facility to be able to print the macro variables at a particular coordinate in space, which is known as a probe measurement. So I would want to specify a probe in the wake of the geometry in order to be able to study its aeroacoustic behavior in the wake of the geometry. So I'm just going to name it as probe underscore acoustics. Sorry. And the only parameter that is of interest to me is pressure. So I'm just going to select pressure. The x coordinate is 1.4, y coordinate is 0.25, and z is 0. So as you can see, the probe lies here. Let me just increase the size. So this is where my probe lies, and at this particular point, I will be able to monitor the pressure with increasing time. So this gap time is basically the frequency at which I would want my data to be printed. And I'm going to specify a frequency of 0.006 seconds, which is basically the time that my flow would need to cross the characteristic length of the vehicle, which is the width of the vehicle. So I'm just going to click on apply. Similarly, we also have volume measurements where data for the entire volume of simulation will be printed into ParaView friendly files, which can also be post-processed in our post-processing tool. So I'm going to just add a volume measurement, call it volume underscore data. And I would want to be able to monitor the velocity to be able to post-process this data to validate it against existing data in the reference. So I'm going to give the same frequency as I did for the probe data, which is 0.006 seconds. And click on apply. Similarly, we also have a facility to be able to print surface data, which is basically printing all points that corresponds to any particular patch in your STL that you might want to monitor the data for with time. For example, you might want to print all points that correspond to the surface that is your tractor trailer to be able to post-process that data to be able to obtain the pressure coefficient, which you can then compare against reference data in your solution. I'm just going to click on plus and call surface data. I'm going to keep the gap time as the same, 0.006 seconds, and I'm going to select the region as fluid. I would want to print both Xmin and GCM as I would want to monitor the velocity and density at the inlet as well, because those would constitute my reference parameters if I wanted to post-process my data for parameters such as drag coefficient, coefficient of pressure, lift, etc. Just going to click on apply. And lastly, we have integrated quantities on the surface of any patch, which are forces and moments, etc., which can then be monitored by the user as part of the monitoring tool that we have. So I would want to obtain the forces on the GCM surface itself. So I'm just going to select the GCM surface and click on apply. Then finally, if you go to the global parameters, we are supposed to set the simulation time, which is the amount of time in the simulation domain that we want our particular case to run for. Wall time is essentially how much time your job will run for this is an upper limit to the number of hours or minutes or seconds that you would want your job to run for. Since this is a test job that I'm showing for demonstration purposes, I'm just going to give a time of 1 hour. And the number of cores is essentially how much compute you might want to throw at your problem. So I'm going to give approximately 640 cores. The project resolution, again, is the global resolution, which is the resolution that is applied at all patches, surfaces, and regions where it hasn't been specified otherwise in the geometry tab or the brush tab of your simulation workflow. So I'm going to give a resolution of around 16 mm. The reference length is basically the distance that your Reynolds number is based on. And for this particular geometry, it's the width of the tractor trailer, which is 0.323 meters. And set restart essentially sets the frequency at which your simulations instances are dumped into storage. These are essentially like saved states that you can restart your simulation from in the future sometime. So I'm just going to set a restart gap. So you can set your restart frequency either in terms of steps or in terms of seconds. So I'm just going to set your restart gap in terms of seconds, and I'm going to give a time of 0.6 seconds. Not 0.6, since that would cross our simulation time, 0.06 seconds. So since this is done, I'm just going to click on generate to see if there's any errors in the simulation workflow. Since there are no errors, I'm just going to click on launch simulation. So this tells me that my pre-submission check has passed and my simulation has been submitted, and the job status shows that it is running. I can check my solver log to see the status of the simulation, and as we can see, it's currently in the meshing state. You can scroll up and choose to refresh your log file to see what state your simulation is currently in. You can also monitor plots once the simulation starts running according to what you've specified as measurements. So your probe plots and your integrated quantities should show up in the monitor plots section of your simulation. So since this might take a little bit of time to start running, I will just run you through the results that I got by running simulations on my own. So I'm just going to jump back to the presentation and show you some quick results that we obtained for this specific case. So this is a plot of the coefficient of drag for simulations that were run at different resolutions for the GCM tractor-trailer geometry at a yaw angle of 0 degrees. So the facility that SankhyaSutra Taral provides the user with is to be able to restart subsequent simulations with twice the number of points for any specific patch as compared to the previous simulation from in the restart instances. So that's how we ran these simulations. We started off with a finest resolution of 3.8 mm, moved to 1.89 mm, and finally we ran simulations for 0.95 mm, where we can see that the error compared to the reference drag is coming down with increasing resolution. And this also underscores the ability of SankhyaSutra Taral to be able to capture the wake characteristics accurately with increasing resolution. Similarly, we also ran simulations for the 10-degree yaw case, which you can read about further in the reference. So this is essentially a plot of the side force coefficient uh, with time. And as you can see, it has an excellent match as compared with the experimental result of NASA. And finally, this is just a sample result of the kind of visualizations that users can generate using SankhyaSutra Taral's post-processing GUI tool. And this particularly is an instantaneous view of the Q criterion that is generated for this particular flow. So yeah, thank you. That has been my demonstration of the GCM tractor-trailer flow and how to conduct simulations on SankhyaSutra Taral for the same. So if you have any questions, please feel free to drop them in the chat window.